Have you ever seen those glowing ribbons in the night sky? That's the aurora, the northern or southern lights. Basically, it's a game of particles and magnetism between the sun and Earth. Scientists call it space weather. But here's the coolest part. The real star of this space show is the air we breathe every day. Today, let's take 5 minutes to break down how these two interact. First, the sun sneezes, then Earth catches it, and finally, the sky starts its magic. Once you watch this, you'll see the most romantic thing in the universe is hidden in the science we know best. The aurora's energy all comes from huge explosions on the sun's surface. The sun is like a giant nuclear furnace, spraying charged particles every second. Science calls it the solar wind. The solar wind travels at about 400 kilometers per second. Do you get how fast that is? In an hour, that's 1.44 million kilometers. Listen up, our fastest bullet train only goes 300 kilometers per hour. Beijing to Shanghai takes about 4.5 hours. But the solar wind is 500 times faster than that train. If the bullet train went at solar wind speed, Beijing to Shanghai would take just 3 seconds. Usually the solar wind is blocked by Earth's invisible shield. That shield is Earth's magnetic field. But sometimes the sun loses its cool. When its surface magnetic activity is very strong, it shoots out a fiercer solar wind. Speeds can hit 800 kilometers per second. Then lots of charged particles break through the magnetosphere and head straight for Earth. These incoming charged particles are mostly electrons. The magnetic field guides them, sliding along the field lines toward the poles. Why specifically the poles? Because that's where the field lines are densest, like the opening of a funnel. It's like drinking through a straw. The narrower the opening, the faster the liquid flows. Here's a concrete example. Earth's magnetic field is like a giant invisible magnet, and the solar wind's charged particles are like iron filings drawn to it. Most particles get pushed away by the magnet's repulsion, like a magnet pushing away paper clips. But a few slip along the magnetic field lines, those invisible magnetic flux lines around the magnet, sneaking into Earth's poles. That's why the aurora shows up near the poles. These sneaky charged particles act like little bullets, slamming into atoms in Earth's atmosphere, inside the molecules. The main forces in the air are oxygen and nitrogen. They get smacked hard by high-energy particles, instantly excited and give off energy. Like when you tap a fluorescent light tube, the phosphor on the tube gets activated and starts glowing. But why are auroras green, purple, pink, all kinds of colors? It depends on what gas gets hit and how high up it is. Green is the most common. It is everywhere. Oxygen atoms get hit at 100 to 300 kilometers up and blast out green light at 557.7 nanometers. Red happens when oxygen goes higher up, above 300 kilometers. When hit, it releases red light at 630.0 nanometers. But the air up there is too thin, so the red light looks dim, often drowned out by the green. What about blue? Purple is nitrogen's show. At low altitudes, 80 to 150 kilometers, when hit, it gives off blue light at 427.8 nanometers. If the particle energy is bigger, nitrogen molecules also throw out pink light. Mixing colors come from oxygen at different heights and nitrogen glowing together. Then the aurora turns purple, pink, or even white. So you see that colorful aurora is really gases at different heights in the atmosphere doing magic tricks like clapping your hands near a light bulb. The filament lights up instantly. But the aurora's trick is way more complex. Particles from the sun dive into the atmosphere and excite oxygen, nitrogen and such, making them glow. Gases at different heights have their own temper. Some love green light. Some prefer to glow purple. That is how we get that flowing painting in the sky. To wrap it up, how does an aurora happen? 3 steps first. The sun sneezes, spitting out a bunch of particles. The magnetic field guides them, sending particles to the north and south poles. Particles smash into atmospheric gases. Boom. Light bursts out. Next time you see aurora photos, you will see right through the trick. The green parts are mostly oxygen atoms working. The purple bits are likely nitrogen molecules helping out. Auroras are not just beautiful sights in the sky. They are also Earth's security alarm. When solar winds get really intense, auroras get brighter and spread wider, that is when satellite communications and power grids might be in trouble. So studying the aurora isn't just to satisfy curiosity, it's also to protect the tech systems we rely on. Want to hear some cool facts about the aurora? Like, can it be forecasted ahead of time? And how intense was the most extreme aurora in history? Let me know in the comments. We'll keep going in the next episode. Hit subscribe. 5 minutes to unlock more cosmic secrets right around you.